In our previous video lesson, we saw how objects that are made up of atoms can be charged as positive or negative, and we said that the charge of an object Q could be either positive or it could be negative. Now, depending on whether electrons are removed, leaving it with a net positive charge, or electrons are gained, leaving it with a net negative charge. So we'd call this charged object positive Q, which was dependent on the number of electrons removed. We'd call this object negative Q, which would be dependent on the number of electrons gained. Now, once this is achieved, the objects have different potential energies, and we say that a high potential energy represents an object that has got a positive charge, and a low potential energy means it's got a negative charge. So we can say there is a potential difference between these two charged objects. Then we said if we take a conducting material and we placed it between these two conducting objects, let's say, then there would be a flow of charge, and if the positive charge was to move, it would move from high to low potential, but if the negative charge was to move, it would move from low to high potential. Now, this flow of positive charge we call conventional current, and the flow of negative charge or electron flow is a negative current. We went on to have a look at the role that resistance plays, let's say, in the transforming of energy. So if we have charge moving, it has kinetic energy, and this kinetic energy can be utilized by something like a light bulb, which offers a resistance to the charge, and as a consequence we have energy flows to produce, in this case, something like heat or light. So the electrical energy, which is the moving charge, can produce light or heat energy. Now, to transform this energy into light and heat, we obviously need something like an energy supply, which in this particular case would be a battery, and our potential difference within the battery between the high potential point and the low potential point are actually these electrodes that are part of the battery, that is the positive and negative end of the battery. You can see in this case we have a conductor that connects the resistance, which is the headlight, and positive charge or conventional current will flow through the circuit. Now, the kinetic energy of the charge is given up as electrical energy. We can represent this circuit, this model of the circuit, as a circuit diagram. So we've got here our potential difference, V, our voltage, is obviously our battery, and we've got our resistor, which is our headlight, and of course we have the conductor that connects those together, which then produces this closed circuit where we can see the current flowing from the conventional current, that is, from positive to negative, or high to low potential. If we were going to talk about electron flow, then obviously the direction would be anti-clockwise. That would be electrons running from low to high potential. So this is our potential energy source, and please note, because we're talking about the energy, the kinetic energy of the charge, whether that's a conventional charge or electron charge, the unit of the volt is joules per coulomb. The coulomb being, if you can recall, the unit of charge. Now, the negative and positive parts of the terminals here represent our potential difference, and of course this is measured in volts. The resistance in the circuit diagram is denoted as R, and the unit is the ohm. The current in the circuit, you can see here, whether it's conventional or whether it's electron flow, represents the kinetic energy of the charge. And of course, if we're talking about conventional current, we're talking about charge moving from high to low potential. And the yellow part of this circuit diagram represents the conductor. Put it all together, we have a circuit diagram. Let's have a look at an example here how we can calculate currents in circuits. So here we've got a truck battery and a handheld calculator, and it says what is the current involved when a truck battery sets in motion 720 coulombs of charge in 4 seconds while starting the engine. So obviously a lot of charge would be required to start the engine, so let's solve this first part. Now we know that we want to find the current involved, so that's going to be I. The symbol for current in our circuit diagram formulas is I. We have 720 coulombs of charge, which represents our Q, which is our unit for charge, and there's 720 coulombs. And the time this current is acting is for 4 seconds. So on that basis now we can actually calculate the current that's flowing in the circuit, because current, as you can recall in our previous lesson, is a measure of the amount of charge running past a particular point in a circuit in a time t. So we have both Q and T, and it's quite an easy calculation, 720 on 4. So the current, we can say in that 4 seconds, is 180 amps. Let's have a look at part B. How long does it take 1 coulomb of charge to flow through a handheld calculator if the current that is flowing is now 0.3 milliamps? Oh, by the way, this 180 amps actually means 180 charges are flowing per second. Okay, back to part B. This time we want to find the time. We're asked to find how long does it take if we have this 0.30 milliamps, which is the current, and we've got 1 coulomb of charge, which is Q. So 1 coulomb. Now again, please note here, because this is milliamps, the multiplier is by 10 to the minus 3. So that'll be a current of 0.3 by 10 to the minus 3 coulombs per second. And that gives us 3.3 by 10 to the 3 seconds. So that's how long it takes 1 coulomb of charge to flow. So let's analyze a circuit diagram. So we've got our potential difference, we've got our conventional current flow, which is clockwise, high to low potential, and of course our resistor. Now mathematically, there is a relationship between the current and the voltage, because in this case the resistance is constant. In other words, it doesn't change, but obviously we can change the voltage, and as a consequence of changing the voltage we're going to change the current. So this is an application of Ohm's law, and it shows the relationship between current and voltage given we have a constant resistor. So this resistance should not change as long as the current is flowing. Now if we were to draw a graph, let's say we were to increase the voltage. So if this is the independent variable, so we're changing the voltage by so many units, and we want to know what's going to happen to the current. So this is the dependent variable, so our volts and our amps. Now what we find is there's a direct relationship. So if we were to collect some data and plot that data, then we'd get a straight line. Now you may have seen this before, maybe in grade 9, but if we were to take the gradient of this line, mathematically we call the gradient m, which in this case represents the resistance in fact, and since the resistance is a constant we can actually determine the magnitude of the resistance. So this is our run and this is our rise. So what we have is the gradient is our rise over our run. So we can produce a quantitative measure of the resistance as we increase the voltage. Now, we say the charge flows from high to low potential. If it was electron flow, then it would go from low to high potential. That's just a reminder of both methods would give us the same relationship between current and voltage, whether we call it conventional or whether we call it electron flow. So in fact, these processes, so conventional current and electron flow, they're really opposite processes. Mathematically, they give us the same quantities. So since the resistance can be determined from the gradient of a graph of current versus voltage, we can determine the resistance of a electronic device in a circuit by changing the voltage, measuring the current, and then finding the gradient to work out the size of the resistance. Now, alternatively, what we can do is we can determine the magnitude of the resistance using a voltmeter and finding the voltage drop across the resistance, because in this particular case, as the current comes along, there is an energy drop here we call a potential drop. And if we know the current in the circuit or the voltage, we can actually work out the resistance or the voltage or the current, depending on what information we're given. So this is called a potential drop here, and as the charge moves through the resistor, it gives up energy. So energy transfer occurs. This might be heat in this particular case, or light. And this represents the energy or voltage drop, as I said, across the resistor. Now, it's hard to imagine this because we're talking about charge in a conductor. So, technically speaking, this potential energy here gives the charge an increase in potential energy. Then it gets to this point, and then it loses that potential energy because it's converted to something like heat or light. So the kinetic energy is converted to heat or light. Now, one way of visualizing this is if we look at a circuit in the context of gravitational potential energy. Now, we know with gravitational potential energy, the further an object is above the ground, the higher its potential energy. So if we thought of charge as being at the ground level, so this is the positive charge at ground level, it comes to this escalator which increases its potential energy. So the charge's potential energy is increasing. Now, as it runs along the conductor, it doesn't lose energy. There is no kinetic energy lost because there is no difference in potential energy at any point. But when it gets to the resistor itself, it rolls down this hill, gives up the energy to the resistor, so there is a potential drop across this path here. So we say that here the charge gains potential energy, and it does this from the battery. The potential difference in the conductor at any 2 points in the conductor is 0. Here is the resistor, and this resistor uses the kinetic energy of the charge. It converts it from potential to kinetic energy, and then it can convert it to something like heat. And so we can view this gravitational model as a working model of what would happen if we could see the charge flowing in a circuit. There are two ways that electronic devices can be connected into a circuit. Something like a light bulb, which offers a resistance to the current, can be connected in series, or we can have the resistors connected in parallel. Now, the first thing we need to do is to define how these are different and what effect they have on the current and the potential drop. So let's start with the simple circuit, the series circuit. The battery provides a potential difference in volts, and if we were to measure the potential drop across each of these and compare the drop across each of these to the potential rise or the potential difference in the battery, then what we'd find is that the sum of all potential drops, so potential drop 1 plus potential drop 2, must be equal to the total potential difference that's applied to the circuit. On the other hand, we have parallel circuit, and if we're considering the potential drop across each of these resistors, so potential drop 1, potential drop 2, what we find this time is the potential drop across each of these resistors that are wired in parallel, the potential drops are equal. So the potential drop across here is the same as the potential here, and the potential drop here is the same as the potential here. Now, if we were to consider the current in both these circuits, so let's again start with the series circuit. The current across the circuit remains constant, so as it passes through each of these resistors, I1 is equal to I2 is equal to the total current. So the current here and the current here is equal to the total current in the circuit. On the other hand, when we consider the current in the parallel circuits, when the current comes along here, it actually divides. Now, this is called a branch, or the branch in the circuit. So only parallel circuits contain these branches. As you can see, there are no branches here. So the sum of the currents in and out of the branch must be equal to the total current that's released in the circuit. So we can say I1 plus I2 equals I total. These observations or measurements, if we were to make them in a circuit, are defined by Kirchhoff's rules. Now, there are two laws that are associated with Kirchhoff's rules. The first one is the current law. So the sum of the magnitude of the currents is directed into a junction equals the sum of the magnitudes of the currents directed out of the junction. Now, this junction is the point, the branch point of a parallel circuit. So this current law applies only for parallel circuits. In a series circuit, the current remains constant. So the second law, around any closed circuit loop, the sum of the potential drops equals the sum of the potential rises. And again, this is only for series connections, where the potential difference drop across each of the resistors must be equal to the voltage provided by the circuit.